we are jumping into polynomial and rational functions. You guys got a lot of experience with polynomial functions. We're going to come up with a specific definition so that it applies universally. You've worked with rational functions, although you may not remember what they are, but you've worked with them. I know this for a fact. Okay, we're going to study both of them today. Or not today, this unit. Today we're going to talk about quadratic functions. So at the end of this lesson, you will be able to A, analyze the graphs of quadratic functions, B, write the quadratic functions in standard form and vertex form. I didn't put that in there, but we're going to do vertex form as well. And use the results to sketch graphs of functions. And lastly, we'll be able to find the minimum and maximum values of quadratic functions in real-life situations. So with that being said, what is a polynomial function? So I'll read this, and then I will translate. Let n be a non-negative integer, i.e. a natural number, or x is in the set of, I should say n is in the set of natural numbers. And let a sub n minus 1, all the way down to a sub 2 and a sub 1 be real numbers with a sub n not equal to 0. The function of a polynomial is given by this guy, right here. It is called the polynomial function of degree n. What does that mean in English? So, I got a function, right? And it is going to have this first coefficient cannot be 0. Okay? I call it a sub n because it's a coefficient. Okay? And it is in front of x to some power of n. Okay, so remember, n has to be positive and whole, right? It has to be a whole number, it has to be positive. So this can't be 1/2 or 1/3 or pi or e or anything like that. It has to be a whole positive number. Okay? And then I keep adding terms. The second term is going to be some different coefficient. I call it a sub n minus 1. Again, a coefficient, but it's different from this coefficient, right? This has an n, this has an n minus 1. That's just so I can tell the two apart from one another. Okay? And then that's being multiplied by x to the n minus 1 power. So if this was n equals 5, so if this was 5, what would this guy be? That would be the 4th power, right? And then I do plus dot dot dot, and then plus, I'm doing it on a second line, but it's a continuation of the same equation, or the same function, and then it's a sub 2 times x squared plus a sub 1 times x. I'm not writing it, but that's to the first power. And then plus a sub 0. And I'm not writing it, but I could write times x to the 0 power. Because what's x to the 0 power, Zach? No. Morgan? No. 1. Any number to the 0 power, I should say any non-zero number to the 0 power is 1. But I'm not going to write that because that's Department of Redundancy department. Okay? That's the definition of a polynomial function. Now, do you need to memorize this equation here? No, I don't need you to memorize this equation. but I do need you to have a working idea as to what a polynomial is. Why do you think I show these things to you guys all the time? I was good at math in high school. I was really good at math in high school. But I relied on my teacher to teach me the book. Do you think I could read the math book? Who here has literally read a math book and understood the math in a math book before? Nobody, right? Why? Because this stuff looks like Greek, right? Sometimes it is Greek. Sometimes I'm using Greek letters. But that's why I teach you guys this, so that when you need to really hit the matrices and work hard on trying to understand something, without a teacher around, you can understand these things. Okay? Anyhow, degree. Okay? This is a polynomial of degree n. Okay? If this is a 5, I call that a 5th degree polynomial. Okay? If it's a 2nd degree polynomial, I have a special name for a 2nd degree polynomial. What do I call 2nd degree polynomials? Square is one name I give it, but I'm in math class, so I don't like using squared as much. It starts with a Q. I'm sorry? It starts with Q, ends in quadratic. Quadratic, right? Order 3 would be a cubic. Order 4, quartic. Order 5, quintic. Order 6, sextic. Order 7, septic. Yeah, right. 8, octic, 9, nonic, and so on. Okay? But they're all polynomials. Okay? You'll also hear it sometimes referred to as the order of the polynomial. So if you hear order 2 polynomial, that also means the same thing as a 2nd degree polynomial. We'll use degree, but sometimes they'll throw the term order at you. Okay? Definition of a quadratic function. You know and love this one. Definition of a quadratic function is ax squared plus bx plus c. That is called a quadratic function. Do I expect you to memorize this one? Oh yes, I do. Oh yes. Now, let me ask you this. Is that quadratic function? Jeff says yes. Anybody else agree with him? Anybody disagree with him? I don't see a bx. I don't see a c. What's up, Morgan? Yeah, so if I wrote this, now I got a b and a c, right? It's just a b equals 0 and c equals 0. What about this? What about is that a quadratic? Remember my stipulation from the previous page. Oh, I'm sorry, not from the previous page, from this page, right here. A can't equal 0. A cannot equal 0. It can equal some number that's not a whole number, so I could have 1/3 x squared, but it cannot equal 0. This is not a quadratic function. Okay? Let's move on to the next page. Is everybody caught up with me? Write the notes? All right. I got 2 forms in which I can write the quadratic function. Okay? And I'm going to confuse you here, but I think it's out of necessity. The book calls this standard form? Exactly. That's my question. Because you know who else calls it standard form? Nobody calls that standard form. Nobody. Okay? So we're not going to call it standard form either. Here's what we call standard form. Is this. That's standard form. The ax squared plus bx plus c. This is standard form. Okay? This we are going to call vertex form. So a times the quantity x minus h squared plus k. Why do you think I call it vertex form? I'm sorry, Morgan, what is that? Oh. All right, anybody but Morgan. Why did I call that vertex form? All right, we're going back. Let me ask you this. Paired function, right? Where's the vertex of that function, Zach? It would be the origin, 0, 0. It might help us to remember what a vertex is. Do we remember what a vertex is on a quadratic function? What's the shape of a quadratic function? We're in math class. Parabola, right? If I pointed to the parabola, the vertex on the parabola, okay, I'd be right here. That's the vertex. Well, not necessarily the lowest point, because that is also a quadratic function, right? Is that the lowest point? Right? Yeah. Yeah. And we'll have a more specific definition in calculus for what a vertex is. But right now, we're either going to call it the maximum or minimum of this parabola. Okay? So, where is the vertex on this parabola again? At 0, 0, right? 0, 0. Where's the vertex on this one? Why, Morgan? Okay, let's think about this. Let me give you another function here, so we're dealing with numbers. Okay? X equals 3 times x times 2 squared plus 7. What's the parent function, Dawson? X squared. What are the lists of transformations wrought upon the parent function to get me this? What's the first one, Kai? What is this guy? What's this do? Does it move it horizontally? Does it move it vertically? Does it stretch it? Does it shrink it? Does it flip it? Moves it horizontally. Right. Moves it 2 units which way? To the right. All right. How about this guy? Up 7. So before I move it up 7, I stretch it, right? But right 2 up 7. So where is my vertex? 2, 7. My vertex is 2, 7. Okay. And this is the vertex form. So the actual vertex is encoded in the function. That's why I call it vertex form. Okay? The other one, the one we know and love, we call standard form because, well, heck, that's what we've used that for everything up until this point. We've seen this very rarely until now, right? We've seen it today, but we also saw it the last unit, right? Yeah, we did. Barely. was on the exam. All right, so here's what we're going to do. Now that we have two forms of a quadratic function, we're going to learn how to go back and forth between the two. And there's a reason for it. Each form has its advantages. What's the advantage of vertex form? What's the obvious advantage of the vertex form? I know the vertex, it's in the name, right? All right. So, what's the advantage of standard form? Is it easier to understand? I don't know about that. But I do know this. If I'm looking to use my quadratic formula, do I want to be in standard form? Yeah, I do. Absolutely I do. Right? So there's advantages to both. Okay. But let's go, before we convert this, I want to do some review. First of all, well, maybe not review this time, but what's the vertex of this function? 212. 2 comma 12. Very good. What's the parent function of this guy? Yeah, x squared is the parent function. And what are, here's the main question, what are the zeros of this function? In other words, what values of x make this function equal to 0? Does 2 make this function equal to 0? 2 minus 2 equals 0. Squared is 0. Times negative 3 is 0. Plus 12. So Jet says 4. How did you figure that out, Jet? You just plugged in numbers and guessed it. Yeah, you guessed and checked, which is a good strategy. Okay? Well, let's do this analytically. All right? So let's do 0 equals. I want to know what values make this function equal to 0. So let's set the function equal to 0. 0 equals negative 3 times x minus 2 squared plus 12. So what would be my first step? Minus 12 for both sides. So I get negative 12 equals negative 3 times x minus 2 squared. Then what? Fine. How would I get that x minus 2 squared by itself? Add 3? Divide. There we go. I'm dividing both sides by negative 3. So when I do that, I get negative 12 divided by negative 3 is positive 4 equals x minus 2 squared. What then? Square root both sides. So if I square root the right side, I just get x minus 2. What do I get on the left side, Keely? Yeah, square root 4. Well, what is square root 4? 2 plus or minus, right? Because negative 2 is what? Yeah! The dreaded plus or minus. The dreaded plus or minus. And then I add 2 to both sides, so that I get 2 plus or minus 2 equals x. And can I simplify that? What's 2 plus 2? 4. Or what's 2 minus 2? So those are my zeros. No, 2 didn't work. 0 minus 2 is? Squared is? Times negative 3 is? So the zeros are 4 or 0 equals x. We already talked about transformations in the general sense, but what are the transformations? To the right 2 of 12.
6.
No, shrink. Horizontal shrink. Vertical stretch. And what else? Yeah, what do we call that? Reflect about the x-axis, right? Okay, so we got that. Now, riddle me this, Batman. What's the domain of this function? What's the domain of this function? This is the review part.
All real numbers except for
All real numbers except for what?
1 and 0.
Those break my equation?
Yeah. Wait.
No, they don't break my equation. They just turn the function into 0, right? So it's all real numbers, right?
That was a trick question.
It's not a trick question. Not a trick question. Now, here's the other question I have. We couldn't answer this when I did the review set with you guys, right? But what is the range of this function? Really? So where's the vertex of this? We answered that already, Dawson. 212. Is this a smiler or is this a frowner? This smile or is this frown? It frowns. So let me ask you this. Is the vertex going to be a maximum or a minimum? Maximum. So the range is going to be y is less than or equal to 12.
Oh, yeah. I am mine.
Yay! Yay! Hercules. All right. Oh, but you know what? No. What did I do? There it is. Okay. Does everybody got this? Because I'm going to clear the ink from the page, and we're actually going to do the point of this slide. So, here's what made it a frowner, Dawson. That guy. The reflection about the... So if I take a smiler, right, and I reflect about the x-axis, it's a frowner, right? You like my little pirouette? You should have seen what I did to make the class laugh in the last class. It was terrible. It was terrible. I can't do it. I get fired.
All right.
No, it's not all right. I need this job. All right. Are we ready? Are we ready? All right. Clear info page. All right. So, again, we are taking h of x. H of x equals negative 3 times x minus 2 quantity squared plus 12. Okay. Now, how do I turn this into standard form? This is really easy. Before you distribute the negative 3, PEMDAS for out, right? Parentheses, exponent. So I got to do the exponent first. Okay? So let's do the exponent. Negative 3 times what? Does everybody see where they got that? What's that? It's not the quadratic formula. Quadratic equation or function, right? Which, this is a quadratic equation as well. This is a quadratic equation in vertex form. We're finding the same equation, but in standard form. Yeah, so now I distribute the negative 3, right? So equals negative 3x squared plus 12x minus 12 plus 12. Yeah. Negative 3x squared plus 12x. Now, riddle me this, Batman. Plus 0, but I don't have to write that because I'm not a member of the Department of Redundancy Department. But riddle me this. If this were an 11 instead of a 12, would I have 0 right here? No, I'd have something else, right? Specifically, I'd have -1. Yeah. So don't let this particular case fool you. I'm going to get stuff here sometimes. It just depends on what I start out with. Okay? Now, the fun part. Going from standard form to vertex form.
Oh, I know how to do this. I bet you I can do this.
Do you?
You got it, really. You just gotta take out the.
Okay.
And then you I forget what it's called, but you just do the opposite one.
Yeah, we do the opposite. You're right. It's a little bit different procedure too. We'll go over that. Okay. But first, I want to ask you guys, what is the y-intercept of this function? What is the definition of y-intercept? I had 2 definitions in last unit, right? 2 definitions of a y-intercept. Yes, where a line crosses the x-axis, and then the other one was the value of, bingo, the value of y when x equals 0. Now, let me ask you this. I got a quadratic equation right here, right? So do I have a line? No, I got a parabola, right? So the first definition does not apply here because I don't have a line. Okay? So now you know why I like the second definition better. The value of y when x equals 0. And so, in order to find the y-intercept, I analyze this function at 0, at x equals 0. So I just plug in 0 for x. 3 times 0 squared, 3 times 0 squared, minus 6 times 0, still 0, plus 9. There you go. Yeah, the y-intercept is encoded in here, right? It's encoded here. Just like the coordinates of the vertex were encoded in the other one, the y-intercept is encoded in this one. Okay? So, yet another advantage to standard form. Okay? No, I don't want to do that. I want to do that. Okay. So, the y-intercept. Back to the y-intercept. That is, the y-intercept is 0, 9. Or, I could also write this in function notation, just like this. H of 0 equals 9. Don't just write a 9. Because, where's 9 on my coordinate plane? Up 9 over 1? Up 9 over 1? That sounds pretty arbitrary. Can I get a point on the coordinate plane with just one number? No, I cannot. I need either that ordered pair or I need a function relationship, right? So do it like this, not like that. Don't be that person. Okay. What are the zeros of this function? In other words, what values of x make this function equal to 0? How do we find that for a quadratic function? Set it equal to 0. Okay. So 0 equals 3x squared minus 6x plus 9. Okay. Now what? Is that how we solve quadratic functions for?
Quadratic formula.
We can do the quadratic formula, but is that our first option?
Factor it.
Factor! Factor! How do I factor this?
Two parentheses, below 3.
Pull out 3 first. Why? Because 3 is a factor in all 3 terms. So equals 3 times x squared minus 2x plus 3. Now what? Oh, that equals 0, right? Now what can I do? Before I do that. How do I get rid of that 3? That 3 divide both sides by 3. So this side divided by 3. Let me scroll up. That side divided by 3. 3's go away, right? This side divided by 3 is what? 0 equals x squared minus 2x plus 3. That looks a lot better, doesn't it?
Yes.
All right, now what?
Factor.
Parentheses, right? Okay, now, here's the beauty of this one. How can I multiply 2 things together to give me x squared? X and x, right? That's the only way. How about 3? Forget about the positive or negative right now. What's the only way to give me 3? 3 and 1. Because it's prime, right? Now, it has to be positive. The 3 is positive here, right? That means it's positive. So I either have to have both of these negative, this and this either both be negative or both be positive, right? And because of this guy, they both need to be negative. Does that work? Does it? X squared minus 3x minus x plus 3. I get minus 4x there, don't I? This doesn't work. I can't, yeah, now I can do the quadratic formula. This will be posted. This will be posted. So I got to plug in the quadratic formula. So let's do that then. Should I do the quadratic formula with this or with that? Does it matter? No, it doesn't. Top one, okay. So, x equals
Negative b.
negative b. These guys sing much better than the other class. The other classes got people in choir, and they just completely butchered it. So I'm plugging and chugging A's, B's, and C's in here. So this equals, well, negative 6. The opposite of that is positive 6, plus or minus square root of negative 6 squared is 36, minus 4 times 3 times 9. So 3 times 9 is 27, times 4 is 108.
Exactly.
How do I break this down? 27 is the same as 25 times, or 25 plus 2, right? 4 times 25 is 100. 4 times 2 is 8. 100 plus 8, 108. Over 2a, so 2 times 3, 6. How does this guy simplify? Equals 6 plus or minus the square root of what? Right? How many zeros does this have? 2. Why?
Because you can't have a negative square.
Right. So this guy, what do we call this guy right here? What do we call that number in a quadratic formula? What do we call b squared minus 4ac in the quadratic formula? discriminant. It is the discriminant. Why do we call it the discriminant? It helps us to discriminate. Uh-oh. Uh-oh. It tells me what kind of quadratic function I have. It tells me how many zeros my quadratic function has. If my discriminant is less than 0, then how many zeros do I have? Then I have no, and I'm going to add an adjective here, no real zeros. Okay? How about if my discriminant equals 0? Then how many? Then I have 1 0. I have 1 0. With big M equal to 2. Who remembers what that big M stands for? Not slope, that's little m. Little m is slope. What does big M stand for? You need me to scroll up there? Is that better, Liv? Okay. What does that M stand for? Who remembers this term? Who remembers that term? Multiplicity. You guys have wondered to yourselves, why does that matter? And we're going to cover that in this unit. Okay? The reason we talked about it in the last class, you never found out why we talked about it in the last class. But there's something that we call the fundamental theorem of algebra. And multiplicity has a lot to do with the fundamental theorem of algebra. It's important. That's why we call it the fundamental theorem of algebra. Anyhow, I digress. How about if x is greater than 0? Then I have two real zeros. Okay? So that's what my discriminant tells me. This particular function has no real zeros. Okay? So now, I'm going to erase ink when you guys are ready. Let me know when you're ready. What are you doing, buddy? We good to go? 30 seconds sufficient? 30 seconds. 30 seconds. Why intercept? We will see. All right. I'm going to clear ink. Bam. And now we're going to go back to the whole point of this is to convert this to vertex form. Yeah, you forgot why we were here, because I got on a tangent. There's a lot packed in this page. That's why we spent so much time on it. But we're going to convert h of x, which is equal to 3x squared, is it minus 6x? Yep. Minus 6x plus 9. We're going to convert this into vertex form. Okay? What's that? I think you are. Because I wanted you to answer these two questions. Okay. Now, the first thing I want you to do is to use the associative property of addition and put parentheses around those guys. We're gonna work with these two things and leave the 9 alone. We're not forgetting about them. We're just ignoring them. We're putting baby in a corner for a little bit. Ah, she got that reference. All right, good. All right. So that's the first step. Second step, I'm going to factor my A out. I'm going to factor A out. So in this case, my A is 3. I'm going to factor that 3 out. So h of x equals 3 times x squared minus 2x, and then I'm going to leave a space here. Plus 9. Remember, I'm just factoring out of the parentheses. I'm not factoring a 3 out of the 9 either. You'll see. You will see. Now, I am focused on the parentheses, and only the parentheses. Who remembers how to complete a square? Who gets flop sweat when I mention complete the square? You know what flop sweat is? It's like when you wake up in the middle of the night and you're like sweating, so it's like you had a nightmare, and you wake up and you're sweating so bad that you're just like, that's what I call flop sweat. Well, you ever go to sleep and then you feel like you're falling all of a sudden? You go, oh! Maybe that's it. I don't know. I hate those. I hate those. Because then I don't go to sleep for another 3 hours. You know, there's supposed to be an evolutionary reason for that. It goes back to when we were living in trees and stuff. You didn't want to fall out of a tree, right? Yeah. It is not. Anyhow, okay. So my next step. Take my b term. What's my b in this equation? Negative 2. Halve it, then square it. So what's half of negative 2? Negative 1. Squared, okay? 1. That's what I add here. Okay? Now, can I just add stuff willy-nilly? I either have to add to the other side, or I'm going to do something different, Zach. I'm going to minus 1 right after it. Yep, we're getting there, Dawson. The big reveal is coming. Now, do I want to simplify this? Do I want to simplify that? No, because I end up right where I started. Here's what I'm going to do. I'm going to get this negative 1 out of my parentheses. It's coming, Zach. I promise you it's coming. It's coming. But what do I have to do in order to get that negative 1, Abby? What do I have to do to get that negative 1 out of the parentheses? Did you just say what he said because that's what he said? He led you in a dark place. Into a dark place. No. What am I doing to everything inside the parentheses? What am I doing to everything inside the parentheses? Times it by 3. So if I want to get something out of there, what do I have to do? Times it by 3. So this is going to be, I'll do this in blue, this is going to come out as a negative 3, right? So I'm going to have 3 times x squared minus 2x plus 1 and the parentheses minus 3 plus 9. Now, can I factor the stuff in the parentheses? I'm going to go back to green. Oh, plus 6, right? This 6. But how does this factor? Who can factor that? Can you factor, Bonnie? X minus 1 squared. Okay, let's do it the long way.
No.
So, X, how's that factor? How's X times X? How does this factor? But it's negative. Oh, I'm sorry. It's positive. So it's either +1 +1, or it's -1 -1, right? Those are the only two ways to get a positive 1. But I got a -2. So it's both got to be -1 and -1. Oh, look. X minus 1 squared. Look at that. This is h of x in vertex 4. Where's my vertex? 1/6. What did we call this process? Completing the square. Okay. Now, everybody, catch up on the notes here, and then put your pencils down. 1/6. You mean this negative?
Yes.
That negative?
Yeah.
Remember, list of transformations. This goes what? This sends my function which way? Which one? So if it starts at 0, it goes right 1 on that positive 1, right? Not negative 1, positive 1. Okay. So my vertex is 1,6. Okay. Now, everybody, are you done? Who's done with notes? Everybody done with notes? Okay, you still working on notes? You got it? Me? Ty, you done? All right. All right, we're done with notes for today, but I want to go on a little tangent here. Why do we call it completing the square? Was that one? Maybe. How do we multiply? How do we multiply polynomials? If I do x plus 1 times 2x minus 3, how do I multiply that? I can spoil it, right? What's the other way? Box method, right? Or what I used to call, what I like calling, what I call the area model, because I'm basically multiplying two things to find the area of the whole box, right? I break it down into the individual boxes, and I add them all together, and I got the area, right? Okay. So let's consider this equation right here. X squared plus 10x minus 39 equals 0. Now, last year when we completed the square, the first thing we would do is we would move that 39 to the other side, right? Now, if I drew a picture of this equation, it might look something like this. When I say x squared, why do I call it x squared? Why don't I just say x to the second power? Because x squared is kind of like a representation of what a square with side length of x would be, right? The area of that is, so the area of the square with side length x is x squared. That's why I call it squared, okay? And then I'm going to have a rectangle. Now, side length of this is going to be x on this side. And what about this side? 10x, right? So that is that guy. This is that guy. Okay, now, I want you guys to bear with me for a second. While I erase this stuff, get rid of this. I'm going to split this up in two. I'm going to split this in half. Maybe you can see where I'm going, maybe you can't. But I love this. So if I split it in half, lengthwise, I'm going to have two rectangles like that, right? How wide are they? They're both x wide, right? But how long are they? I split them in half, so they're 5 long, right? Okay. Now, I'm going to take this guy. I'm going to move him over here. Make it the right side, right? I'm going to make that there. I'm going to take this guy. I'm actually going to delete that and draw another. I could just rotate it, but that's cumbersome. I'm going to draw another rectangle, 5x, but I'm going to draw it on its side like that. So this, because I turned it on its side, is x tall and 5 wide. Okay, and this equals what? This equals 39, right? I got some square over here with 39 area. Now, what am I missing? Oh, what's the length of this side again? This is 5, right? Why do I call it completing the square? What do I add? How big? 5 by 5, right? 5 by 5. So how big? 25. So do we know where half of the b term squared comes from now? This is where it comes from. Whoa! Right? Has anybody shown you this before?
It seems to take half of 10 squared, and
That's the number. Oh. Right? But if I add 25 to this side, I add 25 to this side. Right? All right. We will finish this lesson tomorrow, ladies and gentlemen.